Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on chemical energetics. So this is topic 23 for the CIE specification, so that's the Cambridge Internationals. So if you're studying this specification, then obviously you're in the perfect place for you, in the right place to get all the information, all the revision material you need to know for the CIE topic. There is the full range of A-level videos. Obviously this is just topic 23, but there's the full range of topics for CIE on Allery Chemistry YouTube channel. Please hit the subscribe button and that would be absolutely fantastic. Obviously this is for year 2. This particular topic, I think 23 upwards is year 2. I do have, these are just PowerPoint slides. They are available to purchase if you wish to purchase them. Just click on the link in the description box below. They're great value for money and great to supplement your revision, your notes, and will help you to kind of boost that grade as well. So please go and have a look at them on there. I've bundled them up for in inorganic and physical and organic topics, but I've also kind of bundled them as a full year 2 and year 1 content as well. All right, so let's make a start. Let's see what this topic's about. Now, what I will say, and I've said this about quite a few of the, there we are. Okay, so I've said this about quite a few of the topics with CIE, is that a lot of them actually overlap each other. So you'll find there's a lot of content that kind of overlaps with another topic. Obviously, with this being year 2, you really do need to know the year 1 stuff first, or have a good grounding of it anyway. So obviously anything before topic 23 is year 1 content, and a lot of the topics here, in fact the vast majority of them, will rely on you having an understanding of the year 1 content as well. So just make sure that you understand that. I'll try and bridge it as best as I can, but obviously it would help if you had a bit of an understanding of that first. And you'll find helpfully actually CIE have kind of have given the topic names to the same topic. The topic names in year 2 are, the vast majority of them are the same as the ones in year 1, so you can see where there's a link. You can see where the bridging link is with this. So this one we're going to look at, obviously in the year 1 topic we looked at Hess cycles and looking at enthalpy changes and calculation of enthalpy of combustion and formation, etc. And you do need to know that. Here we're going to kind of take it one step further, and we're going to look at a different, it's not a Hess cycle, but it's something that's a little bit expanded. It's an expanded version of a Hess cycle, basically. The principle of using it is the same, but there's just a lot more steps in it. So for that reason, you need to know some additional definitions when we're dealing with what we call Born-Haber cycles. Okay, so here's some additional enthalpy changes you need to know. So you've got enthalpy change of atomization, is the enthalpy change when 1 mole of gaseous atoms is made from an element in its standard state. So again, a lot of these will become a little bit easier to kind of get your head around once we actually do the cycles. A lot of these is just remembering definitions that may mean very little to you at this stage. But when we do the cycle, you say, okay, yeah, I see where that comes in. So so enthalpy change when 1 mole of gaseous atoms is made from an element in its standard state. So you can see here we've got 1 mole of an atom, 1 mole of a substance. It's in a gaseous state and it's formed from the element in its standard state. So in this case, fluorine in its standard state is always F2 and it's a gas. And to keep it balanced, we have half F2. So you must always produce 1 mole. You can't have a number in front of this. Okay, so that's why we put a half there. Okay, but you'll see that a little bit later on. The other one is enthalpy of solution. Again, you'll see a kind of a Hess cycle for enthalpy of solution and enthalpy of hydration as well, which we'll look at in a moment. But enthalpy of solution, as it suggests, is the enthalpy change when 1 mole of an ionic substance, that could be salt, for example, like sodium chloride, is dissolved in the minimum amount of solvent to ensure no further enthalpy change is observed upon further dilution. Sounds complicated. Basically, to keep it simple, we're adding salt to water and we're going to add, imagine you put a thermometer in a glass of water, you're going to add salt to it, there's a temperature change, and what we're going to do is add the minimum amount of sodium chloride to ensure that it dissolves, or vice versa. We have a pile of sodium chloride in a glass and we're going to add the minimum amount of water we can get away with. That will mean that this is fully dissolved, and that is basically the enthalpy of solution. That's all it is. It sounds technical, doesn't it? But it's just basically, adding just enough to get that dissolved completely. And kind of linked with the enthalpy change of with Haber cycle, Born Haber cycles, is lattice enthalpy of formation. Now this is don't get this is not lettuce. I've seen people write the word lettuce before, lettuce enthalpy. I don't know what that is. It's very healthy, but it's not the word that we're looking for. So we're looking for lattice enthalpy of formation. The enthalpy change when 1 mole of a solid of an ionic compound is formed from its gaseous ions under standard conditions. So in other words, we're forming the standard structure, the standard lattice, I suppose, of a salt. This is calcium chloride, for example, is CaCl2. And to make that, we need calcium ions and 2 chloride ions. These are all in the gaseous state, but we're forming ions in the standard state, or the compound in its standard state. And basically this is the energy change to do that. A lot of this is very theoretical, as you can see, because where are you going to get these from in reality? But all will become clear when we do the cycle. The other definition we need to know, I'm going to go into a little bit more detail with this one as well, is something called electron affinity. So electron affinity is the energy change when we add 1 mole of electrons to form 1 mole of atoms in the gaseous state. So this is just the opposite of ionization energy, which you've seen in year 1. So it's just the complete opposite. Ionization is obviously the removal of 1 mole of electrons from 1 mole of substance in the gaseous state. So that's ionization. Electron affinity is basically just doing the opposite. We're adding an electron. So to affinity means to kind of, if you're affiliated with something, or if you have an affinity with something, it means you're kind of connected to it. So electron affinity means you are obviously bonding to it. You're adding an electron to an atom. Now, here, let's have a look at an example here. So we've got chlorine here, which is the gas, plus an electron. We're going to add electron to chlorine, and we're going to form Cl- ion. Now, the first electron affinity energy is minus 349 kilojoules per mole. So we're adding an electron to this atom here, so that's going to release energy. It's not really going to put up much of a fight, is it, to take an electron to form a full outer shell. So that's going to throw out some energy there. Always include your state symbols. Obviously, this is a gas in this case. And the first electron affinity, you've got to be careful here because you will see, again, an example with the second electron affinity. But the first electron affinity always releases energy, okay? So it's always exothermic, it's always negative. So the first electron affinity here is going to release energy, okay? So it's a negative one. So as we go down group 7, we're going to look at some group 7 elements here because these are your common ones, really. As we go down group 7, the amount of energy released by adding an electron to an atom, this decreases as we go down. So you've got fluorine, chlorine, bromine, iodine, and there's your electron affinity values. Now, the reasons why this is, again, linking back to year 1, or the concepts of year 1, is that if you look at fluorine, it is a much smaller atomic radius, okay, compared to something like iodine, which is much bigger, let's say, for example. So remember, when we're adding an electron to an atom, the reason why the electron will kind of stick or kind of be affinitized, I suppose, to the atom is because we have an attractive force in the nucleus which pulls that electrons towards itself. So if that nucleus is shielded by lots of electrons, then the attractive force isn't going to be as strong, and so therefore the kind of energy thrown out by adding an electron to it isn't going to be as good, isn't going to be as high, should I say. That's not the right word to use, don't say good. Not going to be as high. So your iodine is minus 314, and your fluorine, which is this one, is minus 348. So the attractive forces are much stronger here, okay? Now, exception, and you can see here there's a slight exception to this, which is fluorine, okay? So fluorine has the single shell in there. This is a small atom, okay? It's really small, and adding an electron will actually make it really crowded. It's a bit too squashed, and so there will be more electron repulsion. So effectively, we're trying to push an electron into something which doesn't really have a lot of space. It's not comfortable there, and actually it's a bit too close to other electrons, and so therefore it doesn't give out as much energy as, say, chlorine. So just be kind of aware of that. It's just bit of an anomaly there, and the example might pick up on that. It's a point of note, as I say. So that point of note, it probably might be addressed, and they might say, well, what's happening here? So just be prepared for that one. Okay. Right, okay, so let's look at ionic bond strength and energy. We're going to start with what you mean by energy and ionic bond strength, etc. Because Born-Haber cycles, which we'll look at after this slide, is all about the energy involved with ionic substances. Okay, that's basically what it's going to be talking about. And it's the theoretical energy of forming these ionic compounds. So it's a good idea to start with looking at the bond strength and the energy of some of these ionic compounds and what impacts the strength of these. So obviously the size of the charge in the ion affects the strength of the ionic bond, which might sound quite obvious. But basically the bigger the charge in the ion, the stronger the electrostatic attractions between these ions. So if you remember from the bonding topic in year 1, you would have kind of picked up on that. So more energy is required to obviously overcome these forces, so they generally have high melting and boiling points. You should be aware of that bit already really from year 1. So let's have a look. So we've got potassium chloride as an example. This is obviously made of K plus and Cl minus ions. It has a melting point of 770 degrees Celsius, whereas calcium oxide has this double charge, a 2 plus and a 2 minus, and you can see its melting point is significantly higher. And obviously these attractive forces are helping to, the stronger attractive forces, should I say, are helping to push that melting point a bit higher than what we'd probably expect with a single charge. The size of the ion, which is the ionic radii, affects the strength of the ionic bond. So the smaller the ion, the stronger the electrostatic attractions between the ions. So if they're a bit smaller, obviously the forces that attract them are much stronger. So they can pack together a lot more closely. Obviously they're smaller. More energy is required to break them forces, and therefore the melting and boiling points are therefore higher as well. So let's have a look at an example. Sodium chloride is made from Na plus and Cl minus. Okay, melting point of 801. Okay, whereas potassium chloride, now potassium is bigger than sodium, has a melting point of 770. So these ions here can pack together much more tightly and neatly than potassium chloride can, and so therefore that means the melting point is going to be higher. So generally, okay, and this is the general term, the smaller the ion and the higher the charge, the stronger the electrostatic attraction, and hence the higher the melting point. And we basically say they have a high charge density. So the amount of charge to the size of the ion has a big impact in terms of the electrostatic attractions between these ions. Okay, so hopefully you get that, and hopefully you understand, you get your kind of brain now into kind of ionic compounds and looking at them and how they work. Here we're going to introduce you to another cycle. Now, what I want you to do is see this cycle as a bit of a detailed Hesse cycle. It isn't a Hesse cycle, but you treat it in a similar way in terms of how you use it, in terms of calculating enthalpy values for different sections. So Born-Haber cycles, they're really useful to calculate lattice enthalpies. Okay, and this is because we can't calculate it directly from experiments. It's really difficult to do that. So Born-Haber allows us to work out what the enthalpy change would be in theory. So when we're drawing a Hesse cycle, we're going to start by drawing. You've got to draw a basic cycle really, but you draw by writing down your ionic compound that's under examination at the bottom. You draw a big line at the bottom, and you put lithium chloride, which is obviously here, so it's LiCl, and that's a solid. Now, the next line above it, and we kind of make sure you leave space above here, because that's where you're going to draw the rest of your cycle. The next line above it is always going to be, now this might be slightly back to front for some of these bits here, but it doesn't really matter too much. But this one the next line must be lithium solid to half Cl2 gas. So these are the elements in their standard states forming lithium chloride in its standard state. So this is enthalpy of formation. Now we've seen this in year 1 chemistry, okay? So this is basically elements in the standard states forming a lattice and forming a lattice of lithium chloride. Okay, so the next one up, what we're basically going to do is say, right, well, we can form lithium chloride by taking the elements in the standard states and forming it. Fine, okay. We can also form lithium chloride by going a different way. Now this one's a lot more kind of convoluted, but effectively we can form lithium chloride in a different version. So when we draw on this, we can draw the next line above this as the probably good idea to put something called the enthalpy of atomization of chlorine. Okay, so this is where basically we've got chlorine in the standard state and we're going to convert chlorine into a gas. This is a solid, but when you do Bohr-Haber cycles, you break it up bit by bit. So we're going to ignore lithium for the time being and just look at chlorine. So going from half Cl2 gas to Cl gas, that's chlorine atom, then we draw that arrow up and that's atomization. Now the next line up, we're then going to do atomization of lithium as well. So we're going to turn that from a solid into a gas. So atomization is where you're turning it into its standard state like this. Okay, so that's gone from solid to gas. Although we're not changing the actual number of lithium atoms here, we are changing the state, so that's classed as atomization. Right at the top here, we then need to ionize the chlorine, so remove an electron from it, first ionization, to form Li plus, sorry, that should be Cl minus gas there. Ignore that. that's the next step. Lithium is going to remove your electron from lithium, of course, and you're going to obviously produce Li plus with your electron and Cl. See, I'm jumping ahead here, and then we need to form Cl minus gas as well. Okay, so Cl minus is effectively, we're going to take that electron and add it on there. So what we've done is this is our electron affinity. So this is where we're adding the electron that was removed from lithium and add it to Cl minus ion. So then what we're left with is this state here, okay, lithium ion plus and Cl minus ion gas. So this is the ions in the gaseous state, okay, forming lithium chloride in the solid state. Does this ring a bell, do you think, from what we mentioned before? It should do, because this is the lattice enthalpy of formation. So effectively, we can form lithium chloride through reacting it with ions in the gaseous state, which is here, or we can do an enthalpy of formation where we have lithium atom, so solid, reacting with half Cl2 gas. So there's two ways in which, in theory, we can make lithium chloride. One way is pretty straightforward and uses just the elements that we've already got. The other way means we have to do a bit of prep work to kind of form the ions in the gaseous state first and then form lithium chloride. And a lot of the examples, obviously you'll see, we'll put some figures in these and we'll show you how to work them. But the best practice really is to always put this at the bottom. That's definite. Start with the elements. I'll probably go on the left hand side. Start with the elements in the standard states first. Then I would atomize any elements you've got here. So atomize your chlorine, atomize lithium, produce your ion for your metal, and then produce your ion for your non-metal. And then obviously bring that back down around here. Now, the key things here is that just a little bit like, sorry, excuse me. So this diagram shows you an energy profile. So basically, the higher up this kind of scale you go, this cycle, the higher the energy. So these elements here, these constituents here, are the highest energy level out of any step here. This is the lowest energy level. Now, ultimately, reactions want to be, or compounds want to be at this level here. So naturally, we're going to have, moving towards this is going to be much more energetically favorable, and these are obviously going to be exothermic. These processes here require energy to do. So you're putting energy in to turn half Cl2 gas into Cl gas. You're putting energy in to turn lithium solid into lithium gas. You're putting more energy in to remove the electron from lithium, and then you release energy when you add the electron to chlorine, and you release energy again when you bond these two together and form a stable lattice, your lithium chloride lattice. So very much similar to Hess's cycle in the fact that the total energy change of these reactions is the same. It doesn't matter which route we take. So if I start here and I want to get to, let's say, here, okay, I can either go this way, okay, which I go against the arrow, so I flip the sign here for the number, or I can go up here, down here, and then back up here. So the principle is the same, and hopefully you'll see that. Okay, so let's have a look at an example, and here we're going to calculate lattice enthalpies by using the cycle in the same way as Hess cycle. And remember, if we go with the arrow, we keep the sign the same. If we go against the arrow, we change the sign completely. So here we've been given some data. So we've got enthalpy change here, which is enthalpy of formation of lithium chloride, first ionization of lithium, enthalpy of atomization of lithium, enthalpy of atomization of chlorine, and the first electron affinity of chlorine. So this data has been provided to us. Now, I've drawn the cycle out here already because we've seen this cycle, already. They might ask you to draw the cycle. They might give you half the cycle and you have to finish it off. But for this purpose, we're just going to use the figures here. So what we're going to do is we need to work out the lattice enthalpies by using the cycle. So the lattice enthalpy is this. So we want to work out this bit here. Okay, we want to work out that value going down there. So we know it's going to be an exothermic reaction because we're forming a solid compound and we're going down. But we need to know the numbers for each of these different steps here. So this first bit is the enthalpy of formation. So we know that's minus 409 because we've been told it there. This bit here, going from half Cl2 gas to Cl gas, is atomization of chlorine. So that's 242. So that's going to go in there. Now we're going to divide that by 2 because we have got 2 of these. We've got 2 Cl2s. So we divide it by 2 and that should be 121. Just be really careful because we're going from Cl2 to Cl. Okay, so this is the enthalpy of atomization of Cl2. Okay, but we're only using half of it. Okay, so we're using half Cl2, so we've got to divide that by 2. Just be really, really careful with that. Look at the data they've provided you with and don't trip up. Next one is atomization of lithium, which is 161. Straightforward. Ionization energy of lithium, which is the first ionization, is 519, as we've seen there. And then the electron affinity of chlorine is minus 364, which is on the side there. Okay, so we need to calculate the lattice enthalpy of formation of lithium chloride, which is here. Okay, so that's what we want to work out. Now, just like with Hess cycle, what we're going to do is we're going to start from here. That's where we're going to start from, and that's where we're going to end. Okay, which is down there. There we are. Okay, so we're starting there and we're ending there. So we can't go this way. That's what we want to work out. Imagine this is like a roadblock. Now, I used an example in the previous video. I live in Northumberland, so I live in Morpeth. Morpeth is just north of Newcastle. I can get to Newcastle quite a few ways, to be fair. It's quite a big city, so but I can get to Newcastle quite a few ways. One of the major routes into Newcastle is using the A1. So the A1 straight from Morpeth into Newcastle. It's the most direct route, and I can get in there. So this is a bit like me going from Morpeth to Newcastle, going via the A1, and I can get there. Now let's assume the A1 is absolutely chocker at the minute. It's really busy. They are kind of widening the road, but a lot of road works, and quite often it gets really busy. So I still want to get Newcastle, still want to get here, but I need to take a diversion. So I need to go down a different road called the A19. So the A19 is a longer road, but it will still ultimately get me to my same place, the same place where I wanted to go anyway. So Seaborn Haber is a bit like this. So we want to get from here to here. This road's closed, so we need to go this way. We need to take a diversion and go the other way instead. Now, whenever we take a diversion, remember, when we go against the arrow, we flip the sign, okay? When we go with an arrow, we keep the sign the same, and that's literally all we're doing. Just work your way around the cycle until you get to your end point. So we're going against the arrow here, so that's plus 364. We're going against the arrow here, that's minus 519. Against the arrow here is minus 161. Against the arrow here is minus 121. And then we're going with the arrow here, so we're going to keep that as minus 409. And that's literally all you do. You just kind of go around the cycle until you get back to where you are. Once you're there, put them numbers into the calculator, and you should get an enthalpy, a lattice enthalpy of minus 846 kilojoules per mole. And remember, you can start anywhere on the cycle, anywhere you want. Follow this rule, go with the arrow, keep the sign the same, go against it, you change it, and you should always get a value of 0. If you're not, something hasn't gone right. Okay, so just really, really make sure you've got the right figures in there. Okay, so it's always a useful check. So you can get quite a few marks for this. Okay, so let's look at another example here. Okay, so we're going to calculate a different part of the cycle, just to kind of show you this. Keep the principle the same, okay? So we've got some information here. What I would probably do is start by just plugging in some of this information into the gaps here. So let's see if we've got an enthalpy of formation, which we do. Yeah, so lattice enthalpy, we've got lattice enthalpy of formation. We've got enthalpy of formation. Don't get these two confused, by the way. Enthalpy of formation is this one, so that's minus 411, which is brilliant. Okay, we have the enthalpy of atomization of chlorine. It's 242 divided by 2. Remember, they've given us the enthalpy of atomization of chlorine, of Cl2. We only want half Cl2, so we've got to divide that by 2. We need to calculate the enthalpy of atomization of sodium. They haven't given us that information here. The ionization is 496. The enthalpy, the electron affinity is minus 364, and this time they have given us the lattice enthalpy of formation is minus 787. So here we're kind of wanting to work out this bit here. So we're going to apply the same principle, start here, end here. Okay, it's a bit like that diversion I was talking about. So we're going to start here and end here. Now we want to work out that bit. We can't go that way. There's a roadblock because we don't know what the value is. So we have to go down here, up here, and then back down to get to our end position. So literally follow the arrows. So we're going against the arrow here, so that's minus 121. We're going to go against with the arrow, here, so we keep the sign the same as minus 411. Against the arrow here, plus 787. Against the arrow here, plus 364. And then against the arrow here as well, which is minus 496. Literally put all that in the calculator and we should get an enthalpy of atomization of plus 123 kilojoules per mole. Again, check all these values here. They should all add up to 0. Okay, so if you start there and you come all the way back round to where you started from, then that should always add up to 0, always. Okay, so always worth a check. Right, okay, so let's look at a bit more of a complicated one. So this is an extended Born-Haber cycle for ionic compounds that are made up of 2 double ions. So we're going to look at Mg2+ and O2-. Now you can see there's a lot of different things going on here, but I just want to kind of point out a particular quirk in particular. So notice just some differences here. I'm not going to go through the whole thing. I'm just going to point out the differences. So obviously here we're taking magnesium and we're going to ionize it twice. So magnesium can lose 2 electrons to form Mg2+. So the first ionization is here, and then the second ionization is there. Okay, this is an endothermic process. Definitely, it takes a lot more energy to remove the second electron than it does the first. So it's a much bigger step up than this previous one here. Okay, so we formed our Mg2+. The other weird bit as well, it's not quite weird if you think about it, but obviously we do the electron affinity of oxygen here, which is the first electron affinity, is obviously down here, which is fine, you're adding an electron. But then when you want to add a second electron to something that's already negatively charged, i.e. this, the second electron affinity, you have to actually put energy in to do that. So this is an endothermic process. Now, the reason why is you're trying to add a negatively charged electron into something that's already negatively charged, and therefore you have some electron repulsion here. And these repulsive forces mean that you need to put a little bit of energy in to actually get them to get that second electron on the original ion. So, and then obviously what you're left with is Mg2+ and O2-, and then you then draw obviously the final step there. So just a couple of things to look out for. It's this bit here, the second ionization, but it's really this bit here that's probably really important, is anything where you have a second electron affinity or even a third, anything like that, this is going to require energy to do that. Okay, so that's why there's a little kind of blue arrow pointing upwards there for endothermic. Okay, so what we're going to do is we're going to kind of move away from Born-Haber a little bit, and we're going to look at, still looking at Hess cycle to an extent, except this is a special type of cycle. It's not really a Hess cycle, to be honest. It's a special type of cycle. It'll look like a Hess cycle, but it actually isn't. It's a bit like them I'm trying to think, a bit like nettles. You can get nettles that actually are stinger nettles and do have a sting in them, but you can get nettles that look identical to a stinger nettle that don't actually have any sting in them at all. So this is a little bit like a Hesse cycle, but kind of looks like one, but isn't actually, technically one, but you treat it in the same way. You'll see what I mean in a moment. So this is where we're going to look at the other reaction where we're talking about enthalpy of solutions. Okay, so remember, the enthalpy of solution is the enthalpy change when 1 mole of an ionic substance, like salt, is dissolved in the minimum amount of solvent, like water, for example, to ensure that no further enthalpy change is observed upon further dilution. So in other words, there's no change in energy when you're adding more water in there. So that's the enthalpy of solution. So basically we want to work out the energy change when we're adding a solid salt, into water. Okay. Now for a substance to dissolve, there's 2 main things we need to know. So bonds must be broken first. So that's an endothermic reaction. Obviously you're putting energy in to break the bonds, and new bonds are formed. Now that's between the water, if that's the solvent. It could be other solvents, but let's just keep it simple and say it's water. So let's say it's reacting with the water and the substance, which could be the salt. Now that's an exothermic reaction that's going to release heat energy. Okay, so you must remember these 2 concepts. Right, so let's have a look at some diagrams. I think it makes it a bit easier to understand this. So you've got your ionic lattice in solid form here, and you've got your water molecule, which is here. Your water molecule is your delta negative oxygen, delta positive hydrogen, as you can see on there. And you've got your lattice, your ionic lattice in solid form. So this is a giant ionic structure. These you would have seen in the bonding topic in year 1. Okay, so in theory, the first thing we need to do is we need to break the bonds first. So the bonds are all broken up first, and obviously the attractive forces on the water molecule are helping to break these apart. Now that is obviously broken up into free moving ions, and then what happens is then bonds are formed between the water and the ions there. So obviously your delta negative oxygen will be attracted to the positive ions, and your delta positive hydrogens will be attracted to the negative ions. Now we say that these ions are hydrated. Okay, basically they're surrounded by water. Kind of makes sense, doesn't it? So most ionic compounds, they dissolve in polar solvents like water. If you just take table salt and put that in water, you will be fully aware that salt definitely dissolves in water. So we see that in everyday life. So the delta positive here is attracted to the negative ions. The delta negative is obviously attracted to the positive, as we've seen there. And the structure starts to break down. And then the water molecules obviously surround them. We call that hydration. And for all of this to happen, the new bonds formed here, okay, in this bit here, must be the same strength or greater than them ones that have been broken, than the energy required to break it. If it's not, then the substance quite simply is unlikely to dissolve in water. So soluble substances generally are exothermic. They tend to have exothermic, obviously, profiles for this reason, because the energy released is going to be higher if it dissolves readily. For example, in salt water, if you add salt to water, then it will warm up a little bit. Basically, that's what we're saying, because the energy released in forming these bonds here is greater than the energy needed to break them up in the first place. Okay. Now, I know people are probably going to say, well, I add salt to water and it doesn't feel as though it's getting warm when you touch the glass. The enthalpy change is quite small. Okay, we're not talking about big changes. You need quite a sensitive thermometer to do that. Some salts are more obvious than others. If you dissolve some salts in water, you can actually see a temperature rise and probably feel it a bit. But yeah, they do, promise me. Okay, trust you. Right, so let's have a look. Let's kind of put some maths to this. Obviously, it wouldn't be chemistry without adding a bit of maths there. So the enthalpy change of solution, this can be calculated from knowing, 1, the lattice dissociation enthalpy, and 2, the enthalpy of hydration. Now, we've seen enthalpy of hydration already, and we've heard of enthalpy change of solution already. The lattice dissociation enthalpy is a little bit new, but the dissociation, you've seen lattice enthalpy of formation in Hesse cycle. The opposite of lattice enthalpy of formation is lattice dissociation. Basically, it's just breaking the lattice apart. So we can use a cycle to help work this out. Now I'm going to put some little diagrams in just to help visualize what's going on here, because it is a bit weird, okay? So we've got the lithium chloride. We're going to use this as our salt, and there it is there. It's just a solid block of positive and negative ions. Now, enthalpy of solution, okay, is when we take that solid ion and we dissolve it in water, and we have Li plus and Cl minus ions, okay? So, lattice enthalpy of dissociation, okay, so remember that reaction that we talked about before here. So in theory, what happens is we've got this solid ion here, solid ions, they're broken down first into their constituent ions. Now, there is an enthalpy change here because obviously they're forming gas ions. So this is in theory, okay, this is a theoretical model. So this is enthalpy of dissociation, okay, so breaking that up. And then we've got enthalpy of hydration, which is this bit here, is when the water molecules surround the gaseous ions that are formed here, and it forms your hydration enthalpy. Enthalpy change of 1 mole of aqueous ions, which is here, is made from 1 mole of gaseous ions. So this is basically showing you what's happening, okay? So it can either go via here, directly to it, is enthalpy of solution. So basically we're making a solution, or we can dissociate the ions as a gas, and then obviously the hydration of these gaseous ions after that. So the assumptions that we make here is that we do the following. We break the solid lattice up into its gaseous ions first. This is your lattice dissociation, and then dissolve the gaseous ions in water, which is the enthalpy of hydration. That's the assumption that we make. In other words, to form these ions from this, we break them up to form the gaseous ions first, then hydrate after that. So with this, remember, exactly the same with Hess's cycle. This is not a Hess's cycle. I want to emphasize that. I know I've said that before. So you might be thinking, well, there's arrows going all over the place here. This is quite a unique cycle for this type of reaction here. But when we go with the arrows, we keep the sign the same. When we go against them, okay, we change the sign. So there's no difference in terms of that philosophy there. So going with it here, let's say it's 846. Obviously, you'd be given the data to do this. And then going with it here, this is the hydration enthalpy is minus 883. Okay, so effectively the enthalpy change of solution here is minus 37 kilojoules per mole. So we've got a bit of energy that's been produced basically here, but it goes via this step here. Okay, so there are two things that can affect the enthalpy change of hydration. Probably no surprise here. So it's the charge and the size of the ion, as we mentioned before about ions kind of bonding to them. So enthalpy change of hydration, remember, is when you've taken your ions and they're surrounded by the water molecules. Obviously, they're hydrated ions now. So ions with a higher charge, they'll attract these water molecules much more strongly. There's a greater electrostatic attraction. More energy is released when that kind of attractive force is made, which means they're more exothermic. And this is what I was saying about some salts when you dissolve them. They're a little bit more noticeable than others. So obviously molecules that are might have a 2+ charge and a 2- charge, for example, are going to be greater than singly charged atoms. Or ions, should I say. The size of the ion obviously has a big part to play in this as well. Obviously, the smaller ions have a higher charge density than the larger ions, and this means, again, the attractive forces between the ions and the water molecule will be higher. And generally, we can say the smaller the ion, the greater the enthalpy of hydration. Excuse me. So, you can see the diagram on the left, it shows ions that are smaller and have a higher charge density, which is something like this. You can see there's loads more water molecules that are attracted to it, more bonds being created or more kind of interactions being created. This means it's more exothermic, whereas one which is a bigger ion with only a 1+ charge just won't have the same pull really. So this is going to throw out a lot more energy than something like that. So the size and the charge of the ions do matter in terms of the size of the enthalpy change. Okay, so let's look at a different concept. Now, this is called entropy. Entropy is a bit of a bizarre phenomenon, to be honest. I quite like entropy, actually. You've kind of got entropy, and we'll look at Gibbs free as well later on. But entropy And this might sound so unscientific, but entropy is the measure of disorder in a system. And you think, well, hang on, that's surely science is about being neat and precise and accurate and all this stuff. And now you're throwing in this word of disorder. Yeah, okay, it literally is that. Okay, there is some maths obviously involved. There's a bit of science into it. But entropy, which is given the letter S, okay, is the number of ways energy can be shared out between particles. Okay, so the more disorder there is, the higher the level of entropy. Okay, so that's a good thing. Remember, atoms are very lazy. Well, I always keep saying this. They're very lazy. They want to be in the lowest energy state possible. They don't want to kind of, just kind of sit in high energy orbitals. Electrons are the same. Well, it's the same for solutions as well. They don't really want to be stuck in some regimented kind of, rigid structure. They want to be a bit more free-spirited and move around a little bit more. So naturally, that's a favourable position for them to move into. So just get that concept into your head, really, is that actually the more disorder, the more randomness you've got, the opportunity to have more randomness, then the more entropically favourable it is. Okay? So let's have a look, go right back to solids, liquids, and gases. Okay, it gets more difficult than this, don't worry. So, solids, well, you probably might worry, you think, well, I'd rather have it easy. Anyway, solids have the lowest level of disorder. Particles are arranged neatly in rows. Okay, so liquids and then gases are obviously more disordered. I think we can agree on that by looking at them diagrams there. So the number of particles also affects the entropy change as well. So if a reaction is in the same state but more moles are produced, then entropy increases because there are more ways in which that energy can be distributed. Okay, so remember the number of particles in there. Obviously that has an impact on obviously the change of state. So let's have a look at an example. We've got dinitrogen tetroxide producing nitrogen dioxide. This shows increasing entropy. Okay, so we've got a rise in entropy here. So more moles of gas are produced. So you can see here we've got 1 mole of gas here, and we've got 2 moles here. Now there's more ways in which the products can be arranged than this one. We've only got 1 molecule here. So because we've got more gas molecules on the right, then entropy is increasing, and this is favourable. This can kind of shift itself around in multiple different ways than just 1 molecule on its own. Okay, so for a reaction to be spontaneous, in other words, something to just react or it's feasible, even if it's enthalpically unfavourable, i.e. something that's endothermic. Remember, when we look at enthalpy, and we've looked at that previously, endothermic reactions are not really favourable because the products are higher in energy than the reactants, and obviously, it just doesn't. It's not a good position to be in for these atoms. So exothermic reactions are favourable. Some reactions, because you might be sitting there thinking, well, hang on, why do endothermic reactions just happen? Because they do exist, they're around, they definitely exist. But why do they happen? Why is it sometimes energetically possible to produce a product that's higher in energy than what it was at the start, just under normal conditions? And the reason why is it's not just about enthalpy; it's actually about entropy as well. Okay, so a reaction will tend towards more disorder, and hence there's more entropy. Okay, so the more disorder it is, or the more ways in which the molecules can be arranged, then the better that is for entropy. Okay, that's entropically favourable. So entropy, increase in entropy, is energetically favourable. Okay, some reactions that are enthalpically unfavourable, so your endothermic reactions, they can still spontaneously react if the entropy changes overcome any changes in enthalpy. So it's a bit like, I'm trying to think, it's a bit like a tug of war, I suppose. So you've got one side, you've got enthalpy saying that, okay, we're going to pull it to one side, and the other side is entropy. Okay, so it's a bit like saying, right, well, if one side of that kind of tug of war is stronger than the other, then that line is going to move, the line in the middle of the rope is going to move further to one side, even though you've got people on the other side pulling it the other way. The forces are just outweighing that, and you've basically got this battle between enthalpy and entropy. Okay, you've got this kind of two sides to this. So, for example, let's have a look. We've got a spontaneous endothermic reaction is a reaction between barium hydroxide and ammonium chloride. I love this reaction. It's if you've probably done this in chemistry in the lab. You basically mix the two powders, two solids, which is just bizarre, and you kind of mix these two solids together, and it goes to a paste, and then it goes to a liquid. But then you can mix in a little beaker, and you put a little bead of water underneath the beaker, and then sit that on a wooden block. And then what you do is you stir it and stir it. It noticeably gets colder. You can definitely notice it get colder. And what it does, it freezes the bead of water between the wooden block and the beaker, and you can effectively lift it up, and the wood is stuck to the beaker. It gives off a smell of ammonia, which is not great. So you've got to be well ventilated, of course. But anyway, you produce this product. Now, it's definitely an endothermic reaction. This reaction shouldn't go in reality, but you don't need to add any heat to it or anything like that. Literally just do this at room temperature. Literally just mix these two solids together, and we can get temperature drops of about 20 degrees Celsius. It's really, if you can see this reaction, it's a really good idea to see it. It's a really nice one. Summary points: obviously the reaction is very endothermic, and we can notice that, we can see that. Enthalpically, it just isn't favourable. It shouldn't go. It's like a weird reaction. But if we look at the number of moles that we've got on the left and how many moles we've got on the right, okay, so we've got 3 moles of solid, okay, on the left hand side, and then on the right hand side we have 13 moles of gas, liquid, and solid. Okay, so entropically, this is definitely favourable. We're producing many more molecules of product than we did start with reactant. Okay, many more. So we've got loads more there. But also, we're producing a gas and a liquid, which is more disordered than 2 solids that we started with. So obviously, this is definitely, as I mentioned there, this is definitely entropically favourable. And this reaction goes because the entropy forces just outweigh the enthalpy forces here. So this reaction does go. It is feasible at room temperature. So there we are. So you've got to think about 2 things now. See? So it's not just good enough just to think about enthalpy. You've now got to think about entropy. Okay, so sticking on entropy, here comes the mathsy bit. I can hear you kind of groaning and moaning about it, but we've got to have some maths in this, at least. So hopefully there's some nice formulas here, and hopefully we can kind of make this a little bit clearer at least. Entropy is delta S. Now we've got a delta S of the system, okay, is basically the products minus the reactants, okay. That's an easy one, isn't it? It's not too bad. So the units of entropy, S, is joules per Kelvin per mole. Notice it's joules, not kilojoules, okay, just be careful with that one. So it's joules per Kelvin per mole. Entropy values have a standard entropy, which is S in the underground, which you've seen before in year 1. And the 1 mole of substance, so these are the standard values. So the entropy of the system is 1 mole of a substance. We have 100 kilopascals of pressure and 298 Kelvin. So let's have a look at an example calculation here. So we'll bring that same reaction back of barium hydroxide and ammonium chloride. We're going to calculate the change in entropy. Now, what they'll do for entropy is they'll give you some data here. Okay, so we've got the entropy change here of various different substances, as you can see there. So we're going to work out what the entropy is of the products first. So we've got 2 lots of ammonia, we've got 10 lots of water, and we've got a barium chloride being produced. So we've got 2 lots of 192, because that's your ammonia, 10 lots of 70, which is your water, and we've got 124, which is the barium chloride. So that gives us an entropy change of 1208 joules per Kelvin per mole. Now we do exactly the same with our reactants as well. Again, use the data here to work out what your reactant values are. And then basically we put products minus reactants. So your products are going to be this, and your reactants are going to be over here, and this is going to give you plus 591 joules per Kelvin per mole. So this is a positive entropy value, so this is feasible, okay? Don't get that confused with enthalpy. A positive enthalpy value means it's endothermic, and it's not feasible. A positive entropy value is feasible. So it's the opposite, basically, what it is for enthalpies. Don't get them confused, okay? Okay, so the total entropy change, delta S, this can be calculated using entropy changes of the system and surroundings, okay? So what we've seen, obviously, entropy changes of a system, so that's within a beaker, for example. However, the surroundings can change too, and this is because heat energy is transferred to the surroundings or away from it, depending on what type of reaction you have. So remember, your entropy units are joules per Kelvin per mole. So the entropy, or the total entropy change, is the system plus the surroundings. Okay, total entropy change of a reaction. So there's another equation that allows us to calculate the change of entropy to the surroundings as well. So the surroundings is obviously just anything outside of the container that we're reacting, where the reaction vessel is. So the entropy of surroundings is minus delta H over T. Okay, so delta H is the enthalpy change. Okay, now what you must do is convert that to joules per mole. Now normally you'll have an enthalpy change that's kilojoules per mole. In this case, we're going to use joules per mole, so just be aware of that. Temperature is obviously in Kelvin. So let's have a look at some of them examples there, and let's calculate the total entropy change for ammonium nitrate crystals being dissolved in water to form a solution under standard conditions. And we're going to use them equations that we've seen there before. So there's our reaction there. So we've got ammonium nitrate, and that'll form ammonium ions in aqueous solution. Obviously it's aqueous, and nitrate ions. Enthalpy change plus 25.7 kilojoules per mole, as you can see there. So there's your ammonium nitrate, there's ammonium and your nitrate ions. First of all, because we want to work out the total entropy change, so the first thing we need to do is find the entropy change of the system first. Okay, so what's actually happening in the beaker. So remember, the system is products minus reactants. So the products being produced is 146 plus 113, which are these two here. So producing 1 mole of them each. And then minus 151, which is ammonium nitrate, which is at the top there. So total entropy change of the system is 108 joules per Kelvin per mole. But we want the total entropy change, not just the system. So we need to find the entropy change of the surroundings next to what's going on around it. So entropy change of the surroundings is minus delta H over T. So the entropy of the surroundings is minus 25.7 times by 10 to the minus 3. Remember this value here, 25.7. Okay, remember this is the enthalpy change in kilojoules per mole. So that's that value there. We need to convert that into joules per mole because that's what we must use. So we multiply that, which I just put times 10 to the minus 3. Times 10 to the 3, you can multiply by 1,000. So it means the same thing. So it's just, I tend to do that. It's just the way I kind of use these. So it's minus 25.7 times 10 to the 3 divided by 298 Kelvin, and that gives us minus 86.24 joules per Kelvin per mole. So now we've got our system, and now we've got our surroundings. We can now work out the total entropy change for this reaction. So total entropy change is the system plus the surroundings. So we add these two numbers up, and we should get a total of 21.76 joules per Kelvin per mole. So that's the total entropy change for this reaction. Not too bad, is it? Hopefully not. So what we're now going to do, though, make sure you understand this bit, because what we're now going to do is introduce or try and kind of, because these are fine, basically. These are fine in terms of, okay, we know what the entropy is, and we know how to work out enthalpy from year one. But remember I said there's this kind of tug of war between enthalpy and entropy, and then you had to kind of take these into account. Wouldn't it be nice if we had an equation that can kind of mash these two together and you just get a number that can tell you if a reaction is feasible or not at a certain temperature? That would be useful. It does exist, and this is what you need to know. So this is going to be something called Gibbs free energy. Okay, I keep telling you in science, there's a lot of things named after a lot of people. They seem to like naming things after themselves. So this is Gibbs free energy, and this one's a little bit more obvious. Gibbs free energy, delta G, tells us if a reaction is feasible or not. So it basically takes entropy, it takes enthalpy, it puts them into one equation, and out comes a number that will basically tell you, look, will it go or will it not? Yeah, because we can work out entropy and say, yeah, that'll definitely go. But if the enthalpy value isn't favourable, then it might not go. So this kind of resolves all of that and kind of puts it all together. Now, normally when you start mashing these things together, you get a bigger equation, and unfortunately you do in this case. So Gibbs free energy is basically delta H minus T delta S. It's not too bad. Delta H is obviously the enthalpy change in joules per mole. Remember, when anything you're dealing with entropy, please convert it to joules per mole, okay? Because it just makes it so much easier. T is temperature in Kelvin. Delta S of the system is entropy change in joules per Kelvin per mole. So this is the equation we're going to be using from now on to calculate Gibbs free. So the units of change for Gibbs free is joules per mole. And the basic rule is that the reaction is feasible at the temperature stated in theory if delta G is negative or if it is 0. Okay, so that's what we're looking for. A negative value for delta G means, yep, that reaction should go. If it's 0, that means it should go as well. Just that's the point of where it's just feasible. Now, the reason why we say in theory is because even if a reaction is calculated to feasible, you might not observe a reaction occurring. Now, this might be, and again we've seen this in year 1, the activation energy might be too high. It might need some energy put in to get the reaction going in the first place, or the rate of reaction is so tediously slow you can't see anything happen. So a classic example of that is rust. So if you've got a gate that's say like a gate or a railing or something like that, now that's made of obviously it'll have some iron in there. The iron can react with oxygen and water in the atmosphere to obviously to form iron oxide, which is rust. Now you can sit there all day and you probably won't observe anything happening because the reaction is so slow, but you will notice it over a longer period of time that there is a reaction. It's just you're not going to observe it in a couple of minutes. You can sit and watch a steel railing if you want, but it's not really exciting, is it? So that's just an example, basically. So let's have a look at an example. Calculate the free energy delta G for the reaction between barium hydroxide and ammonium chloride at 298 degrees Kelvin. 298 Kelvin, should I say. So we know the following from the previous slides. Okay, so we know that delta S for this reaction is plus 591 joules per Kelvin per mole, and we know that the enthalpy change for this reaction is 164 kilojoules per mole, or 164,000 joules per mole. Okay, so that's the information we know from the previous slide, just to kind of use that. So here we're going to put the numbers in. Delta G equals delta H minus T delta S of the system. So delta H is 164,000, which is the enthalpy change. Remember, that's going to be in joules per mole, minus T 298, and the delta S of the system is 591. Put all them numbers in, and we get delta G of minus 12,118 joules per mole. This figure is definitely feasible. It's negative value, so this reaction will go, and we've taken into account enthalpy and entropy in this reaction here to produce delta G. So that is a feasible reaction. That's what comment we can make on it. Okay, so temperature may have an effect on reaction feasibility. So, for example, some reactions will go, they'll go quicker, definitely if you heat them up because they've got more energy. But it will also have an effect on if a reaction is feasible, if it'll actually go. So remember this basic rule. The reaction is feasible in theory if delta G is negative or 0. So that's the kind of acid test there. So let's look at different scenarios when delta H and delta S is changed, and we're going to find the delta G value for this. Okay, so this is where actually we're not actually going to look at any specific numbers as such. We're going to look at if a reaction is feasible or if it isn't. So let's have a look at the first example. Okay, so remember the delta G equation is delta H minus T delta S, and the exam board might ask you to comment, will this reaction go in theory? Okay, and we're going to change, we're not actually going to give you any numbers, we're going to just get you to content qualitatively rather than quantitatively. Okay, so it makes it easier to see this equation in two halves. Again, a bit like that tug of war. Okay, you've got one side enthalpy and you've got team entropy. So you've got team enthalpy versus team entropy. very similar names, but never mind. So it makes it easy to see this in two halves. You've got the delta H bit, this is team enthalpy, and then you've got the T delta S bit, which is team entropy, which is this side, okay? So we split it down the middle, and imagine that's a bit like the kind of rope, kind of pulling from one side to the other. So that's how we're going to view these, okay? So let's look at this first row right at the top here, okay? Even if, so this one here, if the delta H, this bit is negative, so that half. So remember, the negative value means that enthalpically it is favorable, because that's an exothermic reaction. Delta S is positive, that's a entropically favorable reaction. Okay, so you've got enthalpy, which is favorable, entropy is favorable. Then even if T was at its lowest, which is 0 Kelvin, then delta G would always be negative. So exothermic reactions, that should be B, sorry. So exothermic reactions with a positive entropy will always be feasible whatever the temperature. Okay, so if we look at that, imagine if you put in a value there, let's say that was 100 minus, that's 0. Okay, so that's 0 times by, I don't know, let's say 100 there. Then obviously that's always going to be 0, and that value is always going to be that minus that negative value. So you're always going to have something which is feasible. Okay, so at any temperature. So that's an easy one for you. Okay, so let's look at this second row. Now with this second row, this time we're going to say delta H is positive, so that's an entropically. Delta H is positive, so that's an endothermic reaction. That's the word. That's not feasible. Okay, that's not possible. Enthalpically, it's not favorable. Entropically, so your entropy is negative, so that isn't feasible here. So this is basically saying, right, that's not feasible, that's not feasible. Both factors here just aren't going in its way. So even if T was at its lowest, which was 0 Kelvin, then delta G would always be positive. Okay, so always positive here. So endothermic reactions with a negative entropy would never be feasible at any temperature. Okay, so these reactions just never go. Okay, so we're just looking at these two halves here. So we're saying, right, if that was negative, say if that value was positive and that value was negative, then this value is always going to be positive. Okay, so let's say if that was 100 and that was minus, I don't know, let's say that was 0, for example, and that was 100 there, then 100 times 0 is obviously nothing. So 100 minus nothing is going to leave you with 100. That's going to be positive, always positive. So it's just making sure that you understand that. So you're looking at two sides here, okay? Okay, so let's look at this third column here. So we're going to kind of now gets a little bit complicated here. So we've got delta H is negative. That's a positive. That's a good thing. Delta H is feasible. Okay, so that means it's exothermic. Good. Delta S is negative though. Not good. Okay, so that's not feasible. So we've got one bit which is feasible and one which isn't. But who's going to win out? Who's actually going to have the bigger impact? Now, there's a point at which one team is going to better the other, and that temperature is going to make an impact as to how, which one's going to win out here. So if we look at this third row, freezing water is an example of an exothermic process. Okay, so heat energy is giving out. Okay, but we're going to a more ordered arrangement. So we're going from a liquid to a solid. So it's not a favorable process that. Okay, going from liquid to a solid. So freezing only happens below a certain temperature, doesn't it? So if you have a glass of water and it's at a room temperature now, like I've got some water here, that's not just going to spontaneously freeze at this temperature. Although the process, the enthalpy is favorable, it's favorable to go to form a solid because it releases energy. The reason why my glass of water is not spontaneously freezing is because it's moving from a liquid to a solid, which entropically is not favorable. But that reaction will be favorable if I put that in a freezer at a certain temperature, so below a certain temperature, then that reaction will go, because actually the enthalpy forces will win out at that point. Okay, so let's put some numbers to it as an example. So delta H, let's assume delta H is minus 100,000. Let's say it's there. And let's say delta S is minus 100 joules per mole. These are just some example figures. Let's say we put minus 100 joules there per mole. So at 500 degrees Celsius temperature, okay, so let's say that's 500 Kelvin, sorry, then delta G would be minus 100,000 minus 500 times minus 100. So delta G would be minus 50,000 joules per mole. So that is a feasible reaction. So this reaction would actually go. Let's say if we had a temperature that was too high. Now this is not linking it to water in particular. It's not actually linked with this example because obviously I know that the point at which this freezes is going to be 273. So it's going to be 0 degrees Celsius. But in this example, this is just showing you how we can work them out really. Minus 1500 Kelvin, so at 1500 Kelvin, sorry, using the same figures, then this reaction isn't feasible. So what this is just showing is we're just putting in arbitrary figures for any reaction. It doesn't really matter. And we're just saying, right, well, at this point, this just demonstrates how actually if the temperature is high enough, it might not be feasible and vice versa. So this is just a generic example, but water is an example of this. Okay, so let's have a look at the fourth row now. There we are. Okay, so this one actually is where delta H is positive. That's not favourable because that's endothermic, but delta S is favourable. This is good. Okay, so an example of a reaction would be something like the decomposition of sodium hydrogen carbonate. And this reaction is actually used to make cinder toffee. So, for example, in crunchies, for example, you can decompose sodium hydrogen carbonate. That's an endothermic process. Delta H is positive. That isn't actually going to, that's not favourable. However, we are going from a solid, because sodium hydrogen carbonate is a solid, to a gas. That's a more random arrangement. So that's entropically favourable. But what we're saying is, though, is that one is favourable and one isn't. So at which temperature does it just become favourable? And basically these reactions like this, with this setup, will be favourable above a certain temperature. Okay, so let's put some numbers in as an example. So here we're going to use the same numbers as before. So obviously it's plus 50,000 wouldn't be feasible in this reaction here, and obviously vice versa. So what we're trying to do here with these equations is it's really important that you look at obviously anything negative and positive, or positive and negative. These are either going to be feasible at any temperature, or they're never going to be feasible at all. It's these bottom two here that are a bit more interesting. So anything where you've got negative, okay, these reactions will go, but at lower temperatures, so it'll be below a certain temperature. If you've got positive, then these will go, but above a certain temperature. So it's really important that you can comment on these qualitatively rather than quantitatively as well, because there's no numbers being given here, but yet you're expected to comment on the feasibility of a reaction. So just so make sure you're aware of that. Okay, so let's kind of add the qualitative element to this. So let's have a look at the temperature at which a reaction just becomes feasible. We can calculate this actually, so let's kind of put some numbers to it. And some people probably might feel a bit more comfortable with this because we can actually work it out. So a reaction is just feasible when delta G is 0. So what we can do is rearrange an equation to work it out when delta G is actually 0. So remember, for a reaction to be feasible, delta G has to be negative or 0. So 0 is the point at which it just becomes feasible. So let's bring in the rearranged equation. Now, here what I've done is I've omitted delta G. I've taken that out because it doesn't have a value, okay? So that equals 0. So what I've done with the remaining equation, we've formed a new one, and this is going to be pivotal. Temperature equals delta H over delta S of the system. So here we're going to calculate the minimum temperature required for sodium hydrogen carbonate to decompose. So this was in the making of crunchies, for example, or cinder toffee. So here we've got sodium hydrogen carbonate solid, decomposing that'll produce sodium carbonate solid, water and carbon dioxide. There's your enthalpy change, it's positive, not good. So the substance is your entropy values here for each of the substances. So what we're going to do is calculate delta S first. So delta S is products minus reactants. So put on all the values of your products there, all your reactants, as you can see there. Entropy value, it comes out with 335 joules per Kelvin per mole. So we're using this data here. Okay, so entropically, that's positive, so that's favorable. Okay. Now, assuming that delta G is 0, because that's the minimum value, that's the maximum value it has to be for a reaction to be just feasible, then T is delta H over delta S. That's 129,000. Remember, that's kilojoules per mole. We must convert that to joules per mole, divided by 335, and that will give us a minimum temperature at which this reaction is feasible of 385 Kelvin. So this is the minimum temperature for this reaction to proceed, and you might be expected to do that as well. Okay, and that's the end of that, which is chemical energetics. Loads of information in there. Make sure you're familiar, obviously, with them equations. Like I say, the full range of A-level topics is for CIE is available on the Allery Chemistry YouTube channel. All I ask is you hit the subscribe button. Massively appreciate that, just to show your support. Also, these are available to purchase, like I say, as a suite of revision slides for you to use. They're great value for money when supplement your revision. If you click on the link in the description box below, you'll be able to get a hold of them there. But that's it. Hopefully that was helpful. Okay, bye-bye.